In this video, we will revisit the topic of inclined planes and friction. In particular, we will look at a few problems on inclined planes and friction. Problem 1. A force F, that is this force right there, acts on a block as shown. The weight of the block is 45 newtons, so we are referring to this block. The block is initially at rest on an inclined plane with an inclination angle of 17 degrees. So this theta here is 17 degrees. The coefficient of static friction is 0.49 and the coefficient of kinetic friction is 0.31. So these two coefficients are the coefficients of friction for the surface between the block and the plane. Now, what is the friction force on the block from the plane if this force here is 4 newtons, 7 newtons, and when it is 17 newtons? Now, the first step is to determine under each of these forces separately if the block will move. So let's first sketch the free body diagram. The force F is shown. The other force that acts on this block is its weight that is acting vertically downward, and that is 45 newtons. We also have friction that is opposing the motion. So let's label the friction that way. Now, it could be kinetic friction, it could be static friction. If there is no motion, the friction is static friction. If there is motion, then the friction is kinetic friction. Now it helps to show the components of 45 newtons, the two components. One component is parallel to the plane, as shown by this W parallel here. And the other component is the component of that 45 newtons that is perpendicular to the plane, that acts like that. So let's label it W perpendicular. Now, from our previous videos, we have shown how to determine these two components. W parallel is quite simply the weight times the sine of that theta, which in this case is 17 degrees. And W perpendicular is a 45 cosine 17 degrees. The next step is to determine the maximum static friction between the block and the plane. And that is given by the coefficient of static friction times the normal force. So in this case, the normal force is the force that acts like that. That's the normal force right there. And the magnitude of this normal force must be the same as the magnitude of the component of the weight perpendicular to the plane. So in this case, since the coefficient of static friction is given as 0.49, and the normal force is given by this component, which is 45 times cosine 17 degrees, and that's going to give you a value of 21.1 newtons for the maximum static friction that could act between the block and the plane. So if the downward force, which is the sum of this F and W parallel, is less than the maximum static friction, the object or the block will not move. If the sum of F and W parallel is greater than F as max, then the object will slide. Another thing to recall about static friction is that static friction is given by inequality. So the maximum static friction is mu sub s, which is the coefficient of static friction times the normal force, and this upper limit is given by that value. More strictly, we can write the value of static friction to be greater than 0, but less or equal to, in this case, 21.1 newtons. So let's do part A. In part A, the force is 4 newtons, which means the downward force is given by the 4 newtons plus the component of weight parallel to the plane, which we know is that much, which is 45 times sine 17 degrees, and that will be 17.2 newtons. Now, this is obviously less than 21.1 newtons, which means the object is not moving. So since the object is not moving, the type of friction that is acting on this body now is static friction, and the value of the static friction must be the same as the sum of these two forces, which happens to be 17.2 newtons. So the answer in this case, the friction that is acting on this body is static friction with a value of 17.2 newtons. Now for part B, now F assumes a value of 7 newtons. So that means the forward force, a downward force, is F plus W parallel, and in this case the sum becomes 20.2 newtons, which is less than the maximum static friction. That means the object is not moving, and the friction that is acting on this object at this moment is a static friction with the same value as that downward force of 20.2 newtons. Note, for part C, F now is 17 newtons. So the amount of force that is acting on a block that is trying to drag it downward is 30.2 newtons. Now note, this value is greater than this maximum static friction. So what that means is the object will now slide downward. So as the object is sliding, which means it is in motion, the type of friction that is acting on this object now is the kinetic friction with a value of coefficient of kinetic friction times the normal force. And normal force is the same as the component of weight perpendicular to the plane, and that will become 13.3 newtons, which you get by multiplying the coefficient of kinetic friction 0.31 with the component of weight perpendicular to the plane. And that solves the problem. Problem 2. Two blocks, A and B, each with the same weight of 30 newtons, are held in place on a frictionless incline with an angle alpha of 20 degrees. Find the tension in the rope connecting the blocks, so that is that rope right there, and the tension in the rope that connects block A to the wall, that is this rope right there. Step 1 is to sketch the free body diagrams for these two boxes, or these two blocks. So let's start with block B. So for block B, you have a block B right there. Now the forces that is acting on block B is the tension on this rope right there. Let's call that tension T. And of course the weight, which is vertically downward, and that we know it's 30 newtons. And of course, this 30 newtons has two components. The first component is the component of that 30 newton parallel to the plane, and the other component is the component of that 30 newton perpendicular to the plane. Now note that this block B right there is not moving. So that means the tension in this rope right there must be balanced by that component of that 30 newton weight. So the tension in the rope connecting the blocks T can be simply written as T equals W parallel. Now we know how to compute W parallel. We take the weight 30 newtons times the sine of that angle, and the angle is 20 degrees, so sine 20 degrees, and that's going to give you a value of 10.3 newtons. Now let's look at the free body diagram of block A. So block A is connected by two strings, or two ropes, 1 and 2. So the tension in this rope has been found, that's T. Let's assume the tension on the upper rope is T1. So in the free body diagram, we should label T1 to be in an upward direction. T, it's going in that direction, downward direction. In addition to that, of course, you have to label the weight, 30 newtons, and the components of that 30 newtons, which is the perpendicular component and the parallel component. So since this block A is not moving, T1 must be balanced by the sum of T and W parallel. So we write T1 equals T plus W parallel. Now we know what T is. T is quite simply W parallel. So T1 is 2 times W parallel. and W parallel is 10.3 newtons, and that would give you a value of 20.6 newtons for T1, the tension in the rope that connects the block A to the wall. And that solves the problem. Problem 3. A block of mass 3 kg, that is the upper block right there, is placed on top of a larger block. So this is the larger block, the bottom one, with a mass of 4 kg. Now, a horizontal force of 10 newtons must be applied to the 3 kg block, that block, in order to cause it to slip on the bottom block. So in order to have a slipping motion between these two blocks, you have to apply a force of 10 newtons on the top block. Now, if the whole assembly of blocks is placed on a horizontal frictionless table, so that means there is no friction right there, what is the maximum horizontal force F that can be applied to the lower block so that the blocks move together? We will start by constructing free body diagram for the smaller block. Since we are told that a horizontal force of 10 newtons must be applied to the 3 kg block in order to cause it to slip on the bottom block, there must be a friction between the surfaces of the smaller block and the larger block. And the friction that we are referring to is the static friction. So among the forces that is acting on this smaller block is you have the 10 newtons to the right, and of course you have this static friction, and it has to be the maximum static friction because under the influence of this 10 newtons, this little block is slipping on the larger block. So the static friction that is acting at that very moment just before slipping must be the maximum static friction. And then of course you have the weight of this smaller block, which is 3 times gravity because the mass is 3 kg, along with a normal force going like that. Let's label it N1. So this normal force is the force that is being exerted by the surface of the bottom block on the smaller block, like that. So that is N1. So just before the slipping motion begins, we know the 10 newtons must be the same as the maximum static friction. So the maximum static friction is given by the coefficient of static friction along that surface times the normal force N1. Now we know what N1 is. N1 is quite simply the weight of the box, which is 3g. So this free body diagram enables us to calculate the coefficient of static friction between the two blocks, and that turns out to be 10 over 3g. I'm going to jot down the value of mu sub s that we have just calculated here for later use. Now let's do the second free body diagram. So the bottom block is a 4 kg and this block is 3 kg. So together the total mass is 7 kilograms. Now we should treat them as part of the same system, a single system. So the weight is 7 times gravity, and now there's a common normal force acting vertically upward like that. Let's call it N2, and let's not forget this force F going to the right. Now there is no friction here between the surface of the floor and the surface of the system, so you don't have to worry about that. However, there is still static friction acting between the surfaces of the two blocks, so we need to remember that. Let's call it F sub s. Now since these two blocks are part of one system, you can assume that the force F that's being exerted is also being exerted on the top block. So in order to find the maximum F that prevents sliding motion of the top block against the bottom block, then the applied force F must be the same as the maximum static friction between the two blocks. And the maximum static friction is given by that expression. Substituting the values of mu sub s and N2 in here, we get that, and that gives you 23.3 newtons. Note that the value of n2 is the same as the weight of the system, and that solves the problem.